Testing, testing. I hope this works. Okay. Bismillah. Assalamu alaikum, everybody. My name is Saad Meliti, a third-year medical student. And today, inshallah, I'm very excited to be presenting the BEP post-midterm crash course. Here's my email. I don't know if any of you guys are using this, but this is very important. This is my number. I'm assuming a lot of you will have a lot of questions because the most important thing in BEP, let me tell you guys, it's definitely past papers. Go through those, memorize them like your name. Not really. It's not like the actual questions themselves are repeated a lot, but the concepts get repeated a lot. And it's important to know exactly what concepts they're testing for on the exam. And I'm trying my best here in this crash course to also include all of that content that has been repeated in past papers and whatnot. So definitely your best friend for this is past papers. This crash course, shout out last year Khalid Jamil's crash course. Although some lectures have changed, it's still amazing. I suggest, since I'm going through the more explanation side of things, Khalid Jamil kind of just gives you the zibda, he gives you the butter. You can skim through his slides if you want a quick review. And yeah, last but not least, I do recommend also just going through the slides one time before your final. It's definitely important. But yeah, if you guys have any questions, because I assume you guys will, if you guys look at the past papers or anything, just hit me on my number, ask me the question. I'll be more than glad to answer. So let's actually get started with the crash course. The first lecture post-midterm is confidence intervals, okay? And I want to explain the concept of intervals to you guys. So to start things off, the confidence interval just gives you a range of possible values for the true population mean based on your sample. Okay, so you take a sample, and this confidence interval is going to give us a range from the lowest end to the highest end of where the true population mean could possibly be. Now, for this course, mainly we're going to be using a 95, but sometimes he might want you guys to use the 90% interval. Okay, but I'll teach you guys about both. So let's say, for example, we're taking a sample of 9 Al Faisal medical students, okay? And we find out that their mean systolic blood pressure is 150, probably because of all the studying, okay? Now, for this population, the known standard deviation is 6, okay? So this is our sample mean, 150. 9 Al Faisal medical students have a systolic blood pressure of 150. But what is the true population mean of Al Faisal medical students? Is it here? Is it here? Is it there? Is it there? We don't really know. And that's why the confidence interval at least gives us an idea of where the true population mean could be. So here is the confidence interval. Now, you can see that it starts from 146.08 and goes all the way to 153.92. Now, in this interval from 146 to 153, we are 95% confident that the population mean or the parameter lies in this range, okay? So once again, the mean could be here, the mean could be here, but at least now we have a range. We know that at least we're 95% confident that it's from here to here, okay? So to define the confidence interval properly, we say that 95% of randomly selected samples will have a calculated confidence interval that contains the true population value, okay? So 95% of the time, our sample that we take and we calculate will have a confidence interval that will contain the population value, the true population mean. But what's incorrect to say is that the interval we calculate has a 95% probability or a 95% chance of containing the true population value. This is completely wrong, or at the very least, it's technically incorrect because the true population value is either in the thing, I can explain here. This is our confidence interval. Now the true population mean is either in the confidence interval or it's outside the confidence interval, okay? There's no such thing as saying and it has a 95% chance of being in it. That's technically incorrect. What we're trying to say here is that once again, 95% of the confidence intervals we get from, any sample we take, or when we take, we're 95% sure that, any sample we take from this population will have a confidence interval with the population mean 95% of the time. 5% of the time, the population mean will be outside of the confidence interval. Sorry, I lost my train of thought there, but I hope that makes sense. So once again, 95% of randomly selected samples will have a calculated confidence interval that contains the true population value, okay? So how do we actually calculate the confidence interval? So I want to give you guys a quick summary, but another thing I want to mention is that I do expect you guys, before watching this post-midterm crash course, to at least have some knowledge of pre-midterm, because a lot of post-midterm kind of relies on pre-midterm. So I will give you a quick rundown on SEM again. So systemic error of the mean or whatever it was gives us essentially the standard deviation, but for means, okay? So when we take a population, when we take a sample, we get this distribution curve, as you guys know. The distribution curve, though, is for specific values. So 100, 110, 100, what's it called? 90, okay? But these numbers are specifically for specific people, individuals that we take from the sample. But when we take the SEM, okay, the SEM is basically this, okay, but for means, okay? So let's say most samples we take from the population with this same sample number. Let's say we have a sample number of 9, okay? Most samples we take with this sample number will lie at 100, okay? Because it's the most common sample mean, okay? But, you know, sometimes we can have a sample mean of 110. Sometimes we can have a sample mean of 90. That's the SEM. It basically gives us this distribution curve, but for means, okay? So in our example, we had 150, right? Okay, so 150 is in the middle. So most of the time, if we take this sample of a Faisal students, a sample of 9, and measure their blood pressure, most of the time we'll get a mean of 150. But sometimes, we can get, you know, a mean of 155, a mean of 145, and elaborate on that further. Because of this standard deviation concept, we can use z-values to calculate the confidence interval. So to quickly calculate SEM, this was the equation. It's standard deviation divided by square root of sample number, or n. So very simply, we just do 6 divided by square root 9. Square root 9 is equal to 3. So we get an SEM of 2. Okay, as simple as that. So because our SEM is 2, okay, now we know basically the standard deviation, but for our mean, if that makes any sense. So for example, our sample mean was 150. But if we go one z-value to the right, we have a, what's it called? We go up by 2 because our SEM is equal to 2. So we go to 152. If we go 2 z-values to the right, we go up by 4. So plus 2 plus 2, 154, okay? So because of that, if we treat this like a normal distribution curve and we use z-values, we can then, you know, figure out exactly where 95% of the means are going to lie, okay? And we can also find out where 2.5% of them on the corners will lie, okay? So we can isolate this 95% here by using z-values. So to do that, we're going to look at our z-table, okay? And as you guys probably know, we're going to look for 0.025, okay? So 0.025 just stands for 2.5%, okay? So we want to, once again, look back at this. We want to just find the tail in which, or the z-value in which, you know, it separates 2.5% from this huge 95% on both ends, obviously, okay? So over here, we found 22.5%. And this z-table is just basically giving us, you know, the 2.5% that's here, right? So in that case, now that we found this number, we have 1.9 and 0.006. So the z-value we're looking for is 1.96, okay? Perfect. So if we multiply 1.96 times the SEM, which was 2, we get 3.92. Perfect. So now we know exactly by how much, you know, the difference is for us to reach that 2.5% point, okay? I'll explain later on a picture. So if we take 150 and add 3.92 to it, and we take 150 and minus 3.92 from it, we get our confidence interval. We get our perfect confidence interval, 146.08 all the way to 153.92. This is our confidence interval. It's our 95% confidence interval, okay? And notice that we're using the z-value negative 1.96 and 1.96 over here, okay? And if you guys didn't understand, the butter of it, the gist of it is that we use these z-values, which is specifically 1.96, to separate this 95% where we're going to find 95% of the means to get the 95% confidence interval, okay? I hope that makes sense. Now, let's say the doctor says, give me a 90% confidence interval. We're going to go back to the z-table and we're going to find 0.05, which stands for 5%. So now we're taking the, the distribution graph, and basically making a line here and dividing 5%. And then over here is 90. And then over here's another 5%. Okay, so we're making a 90% confidence interval here. And the z-value specific for this is 1.6, 0.04. So this corresponds to 1.64. That's our z-value. So if we do the exact same thing, exact same process, okay, that I mentioned earlier, and multiplying the z-value by times to the SEM, then adding it and minusing it to the mean, we get another confidence interval, but this time this is the 90% confidence interval. So we're 90% confident that the population mean lies within these values, which is 146 to 153. And obviously the z-values here represent that, okay? I hope that makes a bunch of sense. Now, if you guys did not understand anything, because it's really hard to explain math sometimes, the general rule is that the confidence interval, okay, is the mean plus and minus 1.96 times the SEM, okay? Now, 1.96 is assuming we're looking for the 95% confidence interval. If we're looking for the 90% confidence interval, that's when this number would be replaced by 1.64. I think we talked about that earlier, 1.64, right? Yep. Okay. So once again, if that didn't make sense, the best way to actually learn is to solve. So we have a study sample mean was 23 with a sample size of 81 and a standard deviation of 18. Using z equals 1.96, what would be the 95% confidence interval? So what we have here is we have the sample mean, which is 23. We have the sample size, which is 81. We have the standard deviation, which is 18, okay? The first step we're going to do once again is what? Calculate the SEM. So SEM is equal to, what's it called? 18 divided by so 18 is the standard deviation, divided by the sample size square rooted, so 81. Square root of 81 is just 9, unless I'm stupid. So 18 divided by 9 is just equal to 2, okay? I don't want to look stupid here, so I'm not going to check it with a calculator. Let's just assume the SEM is equal to 2. I hope it is. Okay, so the SEM here is equal to 2. So now that we know the SEM is equal to 2, let's calculate the confidence interval, okay? So what's it called? The study sample mean was 23. So let's just go to this black thing here. 23, SEM is equal to 2. The z-value is equal to 1.96. So what we're going to do is what are we going to do? We're going to take the mean, which is 23 plus, okay, or sorry, at first it's better to maybe just do minus. 23 minus 1.96 times 2, okay? And then 23 plus 1.96 plus 2, or sorry, times 2. Still it's times 2. I'm stupid, okay? So 1.96 times 2, I'm just going to quickly plug that into my calculator. 1.96 times 2 equals to 3.92. So both of these are just replaced with 3.92. Sorry if my handwriting sucks, by the way. 92. And then we're going to minus it and add it, okay? So 23 minus 3.92 is equal to 19.08. And then that's our first point on the confidence interval. And then at the end, 23 plus 3 is just 26. So 26.92. That's our ends of the confidence interval. That's our 95% confidence interval. We're 95% confident that the population mean lies between these two values. And obviously, in the middle is 23, which is our sample mean, okay? So that's how you solve these kind of questions, okay? Now, obviously, throughout any of this process, I'll show you guys a question at the end of this crash course. He could ask you to find out what the SEM is. He could ask you to extrapolate a lot of values. So understanding this equation is very important to be able to, get any variable if you guys want. I will elaborate more on this in the end. So confidence intervals can be wide, they can be narrow. What's the difference? So if we look here, we have a wide confidence interval. These are wide confidence intervals. And if it's wide, the mean could be all the way here. The population mean could be all the way here. It's not very precise. That's why we say wide confidence intervals are less precise. But on the other hand, when we look at a narrow confidence interval, like this one, for example, the means can't differ that much from each other. So we're very close to honing in on the population mean. So this means it has good precision, okay? Good precision. Tamam? Now, if we take different samples from the population, obviously, our width and position of the confidence interval will change. So our sample mean is going to be different. If we take a different size of the samples, our sample size can change the width of the interval. So if we take a different sample from the population, width and position of the confidence interval can change. And most important to know is what happens if we were to increase or decrease the sample size. So this was our confidence interval with a sample size of 9, right? But let's say we change to a sample size of 25. What's going to happen to our confidence interval? Our confidence interval is actually going to shrink, okay? It's going to become this. Now, you guys are probably wondering, why did my, confidence interval shrink? Well, it's very simple. Because remember, all of this is based on the SEM, okay? Now, our original SEM was 2. But if we use the new sample size of 25, it's going to be 6 divided by square root of 25, which is equal to 5. 6 divided by 5 is equal to, I actually don't know, 6 divided by 5, it's equal to 1.2. 6 divided by 5 is equal to 1.2, okay? So the the standard error of the mean has suddenly decreased to 1.2. So now when we multiply 1.2 by 1.97, okay? Or sorry, 1.96, I think. I'm getting confused now. But basically, this number will be less. And because of this, when we add it to the mean, it's also going to be less. So the whole thing is going to just become narrower. Okay, does that make sense? I hope that makes sense. If it doesn't, someone can text me on WhatsApp. I'll explain again. So basically, but the general concept you guys just have to know is that increasing the sample size will narrow the confidence interval, making it more precise. Now, if we were to decrease the sample size, what do you guys think would happen? The confidence interval would become wider, making it less precise, okay? Now, changing the size of the sample can only change the width, though. Notice how in the previous example, the position did not change. This stayed the same, right? So only the width of the confidence interval changes, not the position. Tamam? So how do we use this thing? Well, first off, I just want you guys to know that p-values aren't flawless, okay? P-values have flaws, and we want to make sure we're considering effect size. So for example, if we're looking at a drug and its effect to, reduce blood pressure, we want to make sure it's reducing blood pressure by a clinically significant amount, like for example, 10 millimeters mercury, okay? If a drug is statistically significant, but it's only decreasing blood pressure by 3, what's the point of it? You know what I'm saying? So we can have a small p-value, okay? Which means it's statistically significant, and a large effect size, and that means we did a good job. We found the large effect size. But if we have a small effect size and still statistically significant, we're confusing statistical significance for, scientific importance or clinical significance. You'll notice that there's a lot of research out there where drugs are being, drugs are being found as statistically significant to older therapies, but doctors are still using the older therapies because the effect size isn't that much. The new drug doesn't really have that big of a difference. Now, on the opposite end of things, if we have a large p-value, which means it's statistically insignificant, but there's a large effect size, we somehow fail to detect a very important drug, okay? But if the effect size is small and the p-value is large, there's no problem. We just ignored something that was small to begin with. Now, we can use confidence intervals to help us out with this decision making. Confidence intervals, okay, help us see, if whether or not it's important, whether or not it's statistically significant. All of this can be easily seen on a graph, right? So over here, you can see a bunch of, confidence intervals. This confidence interval A, first off, notice how it's not touching the null value. And the null value here is 0. So let's say the null value is the null hypothesis. And this drug, for example, does not do anything to blood pressure, okay? But over here is 10. This drug lowers blood pressure by 10, okay? So if the confidence interval was to touch 0, that means we would reject the we would accept the null hypothesis. That means that the drug has no effect. But because of this, because this confidence interval is so high up, it's not touching 0, and it's not touching 10, okay, it's way above it. We know that there's no more data needed to be collected. This drug is statistically significant, so we reject the null hypothesis, and it's clinically important because it passes that importance mark. B, on the other hand, it's statistically significant because it doesn't touch the null value, but it touches the importance value, okay? Now, because it touches the importance value, there's a chance that the mean is under here, like maybe at 8, for example, which means that it's not clinically significant. So we want to actually get more data, and if we get more data, we can maybe shrink the confidence interval enough for it to maybe either, go above the importance line or just, for us to get some conclusive evidence, okay? That's B. So B might need more data. C, on the other hand, doesn't need more data. We can see that it doesn't touch the null value, so it's statistically significant. So technically, we reject the null hypothesis. We'd say that the drug does have an effect. But is it important? No, it's not. It doesn't touch the importance line. Even if we collected more data, it can only, go up to here. You know what I'm saying? The position of the confidence interval wouldn't change, so we're very confident and it's not important at all. Now, D, on the other hand, touches the null value and touches the important value. So this drug is potentially statistically insignificant, but at the same time, maybe it's very important. This study has low power, okay? The power of this study is low. It's inconclusive, okay? Yes, we do reject the null hypothesis. Yes, we do not reject the null hypothesis, and we say that this drug has no difference. But because the confidence interval touches this importance value, you never know. You genuinely never know, and you still need more data, okay? Now, for last but not least, E does not reject the null hypothesis. It's not statistically significant, and it's not even important either. Even if we collected more data, it'll still be either non-significant, or even if it's significant, it won't be important, okay? So it doesn't matter. It's a loser, okay? We don't collect any more data for this guy. Next lecture. Sorry I took so long on confidence intervals. I feel like it needed the most explanation. Hopefully we're smooth sailing from here. We'll find out, I guess. So remember from previous lectures that a statistic is talking about the sample. Parameters are talking about the population. Now we take a sample from the statistic, or we take a sample from the population to make inferences on the parameter, on the population. So we infer the population mean, for example, from a sample mean, okay? That's hypothesis testing. So let's say we're seeing a drug effect on blood pressure, okay? Our null hypothesis in this case states that there's no real effect between the control sample and the sample we're testing. So we're basically saying, and there's no difference between people who take the drug, people who don't take the drug. Blood pressure doesn't change. But and something else to notice is that the null hypothesis is like noted by H0, okay? Our alternative hypothesis, which is H1, states that there is a real effect, states that there is a real difference between the drug and people who don't take the drug, okay? So people who take the drug have a difference in blood pressure from the people who don't take the drug, okay? Makes sense. So the whole concept of, hypothesis testing is we want to see whether this difference in blood pressure, for example, was because of just pure chance or because there's an actual difference. The drug is actually doing something. That's what we want to see, okay? And to do this, what we do is we use something known as the p-value. I think you guys took this in previous lectures. Now, the p-value is just translates to the probability of us getting this result, okay? Assuming the null hypothesis is true. And what I mean by that is, okay, let's assume that this is our distribution of blood pressure for people who don't take the drug and people who take the drug. So we're saying the null hypothesis is true, okay? So the null hypothesis states that there's no difference between people who take the drug and people who don't take the drug. So that means, this is our, population mean, and this is people who take the drug, for example. If we're testing, we're assuming that the null hypothesis is true, okay? And we want to see what are the chances of, for example, if we take, the blood pressure of a patient after taking the drug, we want to see what are the chances of it landing over here, for example, at the far end of the curve, okay? I think I explained this in the slides. So for example, over here in this example, if we assume the null hypothesis is true, that the people who take the drug and people who don't take the drug have the same blood pressure, what are the chances that this is the normal population? And what are the chances that the person who took the drug goes all the way over here? What's the chance that he's this different, okay? So if we look at the chances, okay, we see that the p-value is less than 0.05, okay? We see that there's less than a 5% chance of this happening. That's very rare, okay? We assume, and that's very rare enough for us to actually reject the null hypothesis. So we're saying that it's likely that these two people come from different populations, or that the drug actually has an effect. But if the the population mean and the sample mean here are very similar, and the chance is more than 5% of this happening. For example, this would probably have like a 30% or 40% chance of happening. That's very common. It's likely that these people are actually from the same population, or the drug just doesn't have an effect at all, okay? It's very likely that these people are the same, okay? Now, let's take this a step further. So let's assume that what's it called? Let's assume that the null hypothesis is true. Okay, there's no difference. Okay, and the mean is 120. So the mean is over here. It's 120. Okay, and let's assume we're trying a drug that doesn't work. Okay, the drug actually doesn't work, but subhanallah, by some miracle, okay, the population mean, or sorry, the sample mean ended up here. Okay, their blood pressure. Actually, this doesn't make sense with the blood pressure anymore. I feel like, let's say blood glucose level is actually higher. Okay, so we reject the null hypothesis. We'd say that the chances of this happening are very low. So that's why we're rejecting the null hypothesis. Well, you just made a type 1 error. Okay, we rejected the null hypothesis even though it's true. Now, the chance of getting a type 1 error is actually alpha, okay? Alpha is usually the power of our studies. It's usually 0.05, which translates to a 5% chance. And it's at the two tails, okay? So over here, there's a 2.5% chance of it happening. And over here, there's a 2.5% chance of happening. So that's why over here, it says on the diagram that this over here, this red area is alpha over 2, because it's two-tailed, okay? This is 2.5, this is 2.5. So assuming we're using 0.05, this would be divided by 2, so it's 0.025, and then over here it's the same thing. I hope that makes sense. But basically, in this case, the null hypothesis was true. There is no difference, but b'sudfa, the 5% chance happened, and we ended up rejecting the null hypothesis, which is a type 1 error. But let's assume in this example that H1 was true, okay? The alternative hypothesis is true. And let's say, as you can see, it's very likely that the sample we take ends up here, for example, at 123 or something, okay? Now, if you draw a line, you'll see that it doesn't hit the area of significance. It's not here, it's over here. It's completely valid for us to actually accept the null hypothesis, say that there's no difference between them. Well, we just made a type 2 error. We accepted the null hypothesis even though it's false. Even though this population here is 125 and this population is 120, we said they're the same because by chance the sample we took ended up at 123, and it's just as likely for a sample to be at 123 in this population as it is for this population. Okay? I hope that makes sense. So once again, this is a type 2 error. We accepted the null hypothesis even though it's false. And the chance of getting a type 2 error is known as beta, okay? So beta is all the way over here, all of this. This is huge, by the way. This is the chance of getting a type 2 error, okay? So you might assume, and okay, what if I somehow, stop the chance of type 1 errors by, I don't know, decreasing alpha. So if we try to decrease the probability of a type 1 error, look at this beta graph, look at the beta. The chance of a type 2 error increases, okay? So yes, over here, we're less likely to have a type 1 error because the chance maybe dropped to 0.01 now, but over here, it's so much easier to miss a guy in this, a sample in this population because it's way easier to make a beta error, okay? Because to detect, this population, for example, you'd only have to have like pressure, this is blood glucose, blood pressure, whatever it is, a value above 127 or something, okay? While any other value, although it's valid, would get rejected instantly, okay? So that's why it's a very, it's a balance. And usually we don't even touch the level of alpha. It's very common for us to keep it at 0.005 or 0.05. Okay? Now, if none of the explanation I said made sense, don't worry, you can just blindly memorize right now. So let's say the null hypothesis is actually true. So we're saying, and there's no difference. But let's say we reject the null hypothesis. We just made a type 1 error, okay? And the chance of this happening is alpha, okay? Now let's say the null hypothesis is false, and we rejected the null hypothesis. We made a correct decision, okay? And making the correct decision is known as the study's power, okay? 1 minus beta. So if we go back over here, this is the chance of beta. Let's say the chance of beta here is like 60%. If we do 1 minus 0.6, we're going to get a power of 0.4. So that means our chance of getting or like noticing a difference is 0.4%, okay? That's the power of the study. This is very low. Usually studies aim for 80%, but this is just an example, okay? So 1 minus beta is the power. Oops. So let's say the null hypothesis is actually true and we don't reject it. We made another correct decision. This is known as 1 minus alpha. It doesn't really mean anything, but if alpha was 0.5, the chance of making the correct decision is usually like 0.95, 95% chance. Now, if the null hypothesis is false, but we don't reject it, we just made a type 2 error, okay? So there is a difference, but we rejected it, okay? And the chance of this happening, once again, is beta, okay? We try to reduce this as much as possible, okay? So how can I increase the power of a test? We just talked about this. One thing we could do is increase the difference in means between the populations or make a larger effect size or have a larger effect size. So let's say we have two populations here. If there's a big enough difference, we don't have to worry about these populations running into any errors because they're so wide apart from each other. But if it looked like this and there was a lot of overlap, you get the point. We have a lot of risk for type 1 errors, type 2 errors, all of that kind of BS, okay? So that's why if we had a larger effect size or difference in means, we could technically increase the power. Something we have the most control over as researchers is increasing the sample size. It reduces variability, okay? Another way we can decrease variability is by doing stuff like restricting the age range of the sample or anything of the sort. So usually this is impossible sometimes, but it does help in increasing power. Now, in the last slide, I mentioned effect size. Now, usually the effect size is measured by Cohen's d, okay? It's the effect size for means, okay? So it's mean 0 minus mean 1 divided by sigma, or the standard deviation, okay? So, for example, let's say, now we said that one population has a mean of, what's it called, 120, sorry. The other population has 125, okay? The standard deviation, let's say, is, I don't know, 5. Standard deviation of 5, okay? Let me put the sigma, what's it called, thingy. I can't draw it. Okay. So to calculate, we just literally do 125 minus 120 divided by 5, which answers, the answer of it is 1, okay? Because 125 minus 120 is 5. 5 divided by 5 is 1, okay? So the effect size is 1. An effect size of 1 is actually like an important effect size. It's large, okay? But that's regardless of the point. This is what effect size is, okay? That's how we calculate effect size. Mean 0 minus mean 1 divided by sigma, okay? And the way we decide which one to minus from each other is just, I personally choose the biggest one and then minus it from the smallest one, so I get a positive value, okay? Now, another thing that can increase power is by increasing alpha. Now, this is not really practical. Let's say we made the p-value you need to become significant to be like 0.1. That means there's a 10% chance of a, what's it called? A 10% chance of a type 1 error. So although our power has increased, we're very likely to make type 1 errors, and that's not good at all. Usually journals only accept 0.5 and under, okay? Another thing is doing a one-tailed test. And last but not least is using the t-test, which I will talk about in the next lecture. And there we are, we're at the next lecture. Comparisons of means, okay? So we have two tests. We have the z and the t-test, okay? Now usually, if you guys remember from previous lectures, we use the z-test if we know the standard deviation. If we don't, we use the t-test. Simple, okay? Now, there is a caveat, is that we can use the z-test if the sample size is more than 100, because at that point, khalas, like we have enough of a sample size that it doesn't make a difference. But sometimes it might be hard for us to obtain, a sample size that large. Things like rarity, cost, speed, how fast we want to finish the study, the depth of study. Maybe we're studying patients in super depth, so it's hard for us to do 100 of them, prevents us from having large sample sizes. So that's why we mainly use the t-test. So let's take this other example. A sample of 9 FSS students have a blood pressure of 106. This time it's more normal. Now, they have a standard deviation of 6. Now, please don't confuse this with standard deviation of the population. This is just standard deviation from the sample itself, okay? When we're using the t-test, we don't know the standard deviation of the population. Now, the average person, though, has a what's it called? A systolic blood pressure of 100 usually, okay? So our first step to see if this is significant is to calculate the SEM, as always. So to calculate the SEM, we just do that thing again. We do 6 divided by square root of 9, it's equals to 2, okay? We already did this before. So now that we have the SEM, it's time to calculate the t-value. The t-value is calculated by sample mean minus population mean divided by the SEM. So let's do this. We have 100 minus, 106 minus 100, which is the population mean, divided by 2, which is equal to 3. Our t-value is here 3 here. Because remember, 106 minus 100 is 6. 6 divided by 2 is 3. Okay? So now we have a t-value of 3. So now we run into this huge table. Okay? Now, obviously, both the z-value table and this table will be given to you on the exam. But for now, let's teach you how to use this. So first, we have to find the degree of freedom. The degree of freedom is the sample size minus 1. And we find the degree of freedom. All of the degrees of freedom are written over here. So our sample size was 9. So the degree of freedom is 8. Boom. Oops. Right here. Okay? And we basically follow this line. We go on the line as such. Okay? Now, next up is to find the closest t-value on that row that we just made with a value less than the one we calculated. Okay? We calculated the t-value of 3. So we're going to go along the thing and find something less than 3, but closest to 3. And we find it right here. Okay? So it's 2.8. Okay? Tamam. Now, if we then go up, okay, we go up here, we find that our right tail probability is 0.1. The t-table basically gives us the right tail probability. So what I mean by right tail probability, it gives us the probability of this, okay? The probability that, you find a value in this area, but it doesn't give us this area, okay? So for here, it gave us 0.01. So if we want to find this side, we multiply this by 2. So this is also 0.01. And then we get a total of 0.02. Okay? So our p-value here is 0.02. Okay? So regardless, the chance of this happening is extremely low. It's less than 5%. Okay? It's 2%. So because of this, we'd reject the null hypothesis, and we'd say that there's a difference. We'd say that there's some statistical significance. Okay? So over here, this is some interpretation stuff that they might ask you to interpret in the exam. So over here, he's telling you that T is 8. So this is the degrees of freedom. So from the degrees of freedom, you can find out the population, what's it called, size. You just add 1 to it because degrees of freedom is sample size minus 1. So our sample size is 9. If you just add 1 to 8, our t-value is equal to 3. Our p is equal to 0.02. So this is statistically significant. And our effect size was calculated to be 1. Okay? Which is great. Okay? The 95% confidence interval is 102.8 to 109. Okay, and we can see it here. Okay, now something I'd like you guys to do if you guys want, pause the video and practice, go back to the example I gave you guys. Try and calculate the effect size. I think it's possible. And the confidence interval. If you guys are able to, that means you're doing great. Okay. Now, if you can observe the confidence interval, you'll see that it's not touching the null value of 100. Okay, so that means it is statistically significant. Okay. And that's about it for the confidence interval. There's not really a level of importance that we have to kind of, estimate like in the first lecture. We just know that because it's not touching this null value, it's statistically significant, and the p-value confirms that. Okay? Khalas. So now in t-tests, we have 2 types. We have paired and independent. Okay? So the paired samples t-test can also be called, first off, paired, related, correlated, and dependent, okay, samples, okay? So an example of paired samples are like if we take the same person and measure his, let's say blood glucose before caffeine and after giving him caffeine, okay? So before and after treatments. Or we take the same group and give them 2 treatments. So we give him 1 treatment, then we wait a bit, and then we give him another treatment, okay? The same person, okay? Or we match individuals into 2 groups, okay? Matched individuals in 2 groups. So مثلا if we take 2 twins, one we measure without caffeine, one we give caffeine, مثلا. Or one we give treatment, one we don't give treatment. Obviously it's difficult to get twins nowadays, but what's it called? We can do matched characteristics. For example, we take a 20-year-old female who's blonde or whatever, or this tall, and we get another female who's blonde, 20 years old, this tall, and we do once again give 1 caffeine, give 1 no caffeine, and then compare them as if they're the same person, okay? That's when we can use the paired samples t-test. Now, usually when we're doing paired samples, the data is correlated. So we can see a correlation here. We can see that it's correlated, upward positive correlation. And the 2 groups always have equal size. So for example, if this is, for example, let's say this is height. Let's say that this is before caffeine and this is after caffeine, okay? And we see the values. So this is 100, 120, 150, 170. And then one more example, 160, 100, for example. Now let's say, actually, before you could measure this patient after he takes the caffeine, he just decides, I don't want to take caffeine, and he leaves the study. So you have his blood glucose before you give him the caffeine, but you don't have it after you gave him the caffeine. So because of this, you can't really use this value. You have to delete it. The two groups always have to have equal size. If you have two people before caffeine, you have to have two people after caffeine. Does that make sense? No one's going to answer me, but I hope it does. Now, for independent samples t-tests, two completely separate groups, two completely different people. We give one person the placebo, we give the other person the treatment, okay? Now, the sample sizes can be equal or unequal, and usually this is double blind, and neither the patient or the clinician knows who's taking what drug, okay? And the observations are independent from each other. So one person taking the drug doesn't, affect someone who's not taking the drug, for example, okay? They're all independent from each other. So let's say, once again, we take a sample of 24 of the students, gave 12 of them caffeine and the other 12 a placebo. And we wanted to see if it increased their glucose levels, okay? So here's a table of it. You could plug this into Jamovie or something or whatever the hell. It's just an example. And if we look at the values, we end up with a T 22, so degrees of freedom 22. Now, your first thought might be to assume that the sample size is 23, but we just said that sample size is 24. Why is that? It's because they're in two different groups. So they were divided like this, 12, 12. And each group ran its own test, okay? So the degrees of freedom was 11, 11 for these t-tests. So that's why, in this case, when there's two groups, okay, two tests, our degrees of freedom is actually -2, okay, not -1, okay? So it's actually T22, and then if we add 2, we get our sample size of n equals 24. Now we got a t-value of 1.165, not too important. What is important to note is that the p-value is 0.257, okay? The effect size is 0.48, okay? So you can see that the p-value is very obviously statistically insignificant, and the effect size isn't that big, it's only 0.48. And then if you see the confidence interval, it's -4 to 15. Why is it negative? It's negative because we're comparing the people who took placebo to the people who took caffeine. The people who took caffeine, okay, the confidence interval is touching the confidence interval of the people who took placebo. And since we're comparing these two groups together, the confidence interval overall becomes negative in this case, okay? I hope that makes sense. Now, the fact that this confidence interval is negative already tells you that this is statistically insignificant, okay? The fact that, this confidence interval, goes far into, the other confidence interval tells you that there's no difference in people who took caffeine or people who took placebo, okay? That's how you interpret that. I hope that makes sense. Now, for t-tests, we make some assumptions, okay? First off, we assume that the observations are from a random sample. So we took a random sample. We assume that the participants are independent from each other, okay? And then we assume that the data comes from a normally distributed population. Now, normally, this is only important for samples that are below 25 people, because after you get above 25 people, the sample usually automatically becomes normal, and it's fine. But less than 25, the t-test assumes that the distribution is normal, okay? Now, I hate slides with a lot of text, by the way. I'd kill myself for this, but trust me, I just want to get this over with. The advantages and disadvantages of a paired t-test. I'll get over it very quick. No need to kill yourself over the slide, I promise. So the advantages of a paired t-test is that there's reduced variability between participants. Because we're using the same person, we're not afraid of this person being different from this person being tolerable to the drug more than this other guy. So all of this reduced variability increases statistical power. Crazy, okay? And we need less participants. For example, 12 participants would basically translate to 24 if we're doing a paired t-test, right? Otherwise, like an independent test would need 24 new people, okay? Now, the disadvantages, on the other hand, are the order effect. For example, if you give someone a drug, let's say you give person drug A, and you plan later on to give him drug B. Maybe drug A still has an effect when you give him drug B, and it affects the results of drug B, okay? Now, you can mitigate this by counterbalancing, randomizing, or even spacing treatments. For example, you could give the guy the drug way later on so that drug A has no effect. Alternatively, this might be better. Just use matched pairs or independent samples so that you're using different people and the drug A doesn't affect the outcomes of drug B. There's also participant bias. Basically, a participant, if he figures out what you're trying to test for, he might try and help you in the study. He might try to sabotage the study. Patients are kind of weird sometimes. I don't know why they do that. It's just kind of a human thing. They might, just them knowing what the study is about can already cause bias to the results, okay? Last but not least, there's dropouts. Like I said, losing one participant affects both measurements, okay? And we have to remove both of them because in paired t-tests, you have to have an equal number of participants on both groups, okay? So this can reduce power, okay? Now, independent samples, they vary from each other, okay? So like we said, in paired t-test, there's reduced variability. But when we're doing an independent t-test, we have an issue of variability, okay? The accuracy of the t-test could be affected. But we have the Welch's test to save us. So any program uses the Welch's test, and this kind of, adjusts for this variability between people and helps us do a proper t-test, okay? Properly accurate t-test. Next lecture, analysis of variance. I'm actually losing it. So let's say we have three samples or whatever, three populations. How the hell are we supposed to differentiate between them? How am I supposed to see which one's different from each other? ANOVA. ANOVA can compare the variability within and between means, okay? When we have three or more groups, okay? We can compare variability within and between means. What do I mean by that? First off, let's say I have, I don't know, three means, okay? First off, ANOVA can see the variability within the mean itself, okay? Tell us the variability here. It can also tell us the variability within groups, okay? What's the variability between groups and within groups, okay? I hope that makes sense. So let's say the variance within groups is high. So the variance is high, so the graph is very wide, okay? So and the between group variance is low. So you can see that these groups are meshing into each other, and they're a mess. We'd accept the null hypothesis. We'd say that there's no statistical significance here, okay? We'd say that the groups are the same, okay? But if the variance within the groups is low, so you can see that, they're more narrow because the within group variance is low, and the between group variance is high. Okay, you can see that there's an obvious variance, there's an obvious difference between them. We can reject the null hypothesis. We can be like, okay, there's an obvious difference between these groups, okay? And the thing that tells us that is the F value. Now, the F value, we take the between the group variance and divide it by the within the group variance. So, let's say the between group variance and the within group variance are very close to each other. They're very similar. We might get an F value that's, around 1, okay? If the F value is 1, just remember this, we accept the null hypothesis. We say that there's no difference between the groups. But let's say the between group variance is high, the within group variance is low, like I mentioned in the last slide. We might get a value that is higher than 1, okay? And in that case, we'd reject the null hypothesis. We reject the null hypothesis, accept the alternative. There is an obvious difference between these different groups, okay? So for example, this might be something we reject. This might have, an F value of 1, okay? But this, on the other hand, okay, this has an F value that's more than 1. We'd reject the null hypothesis. These guys are completely different, okay? I hope that makes sense. Now, let's say we wanted to calculate the effect size of this ANOVA, okay? The effect size is calculated by this weird n to the power of 2. Oops, I'm drawing it wrong. I actually don't know how to draw it, but it looks like this basically, okay? I couldn't put it on the PowerPoint. But the way we calculate this, okay, is we take the between group sum of squares divided by the total sum of squares. If you don't know what sum of squares means, don't worry, because I don't know what sum of squares means. The doctor is going to give you the value if he wants to test your knowledge. So if you wanted to calculate the effect size of an ANOVA, you take the between group sum of squares, which in this case is the between group sum of squares is the sum of squares caused by the difference between the groups. So the treatment, okay, the treatment causes the difference. So in this case, it's 648. And then the total sum of squares is we just add these two together, okay? I'm gonna have to use a calculator because I can't do math. So 648 plus 391 is 1039. And if we do the math on this and divide it, 648 divided by 1039, we're gonna get 0.62. So our effect size in this case is 0.62. Oops, I don't know what I just did. 0.62, okay? So that's how we calculate the effect size in this case. Tamam? I hope that makes sense. So the F value tells me that there's a statistical significance, but it doesn't tell me which groups differ from each other. So what do I do in this case? How do I know which groups differ from each other? And like, listen, man, like I have 15 groups to compare. I have to do 105 comparisons. It's crazy, right? So if you guys will notice, as we increase the number of groups, the amount of comparisons we'd have to do increases exponentially. Okay. This was asked, I think, in a question before. I know how much comparisons you'd have to make if you had 3 groups. I don't recommend memorizing the entire table, but like at least, know 3, 4, 5 or something like that. It's very low yield, to be honest. Now, there are 2 types of comparisons. Wait, it's getting a bit hot in here. Okay. There are 2 types of comparisons, okay? We have a priori, planned before data is collected, and we have post hoc, chosen after the data is collected, okay? Now, a priori has more power than post hoc, and why is that? Well, the thing is with a priori is that we're planning these beforehand, okay? There's no chance for us to rig the results. If we're doing a post hoc test, let's say once again I have 15 groups and I decide to do 105 comparisons, okay? The alpha, remember the alpha, the chance of having a type 1 error, it's 5%, okay? So if we do 105 comparisons, there is a 100% chance we might end up, actually getting a type 1 error because the chance of, getting a type 1 error with doing so much comparisons, 105 tests, starts to grow, okay? It's not 5% every time. Like doing 5%, 5%, 5%, 5%, you're bound to eventually get unlucky and have a type 1 error. But for some people, this is actually a good thing. Some people do this post hoc stuff to do something known as p hacking, okay? In which they're going to fish for a significant p-value, okay? That's why if we plan it beforehand, there's much more power because we're not specifically fishing for results, okay? We plan for it beforehand, okay? Now, post hoc tests are meant to at least decrease the risk of getting a type 1 error. So what are the post hoc tests? There are 4 we're going to talk about, I think. So first we have Fisher's LSD, least significant difference, okay, not the drug. It can be used a priori for any number of comparisons, okay? So if we have like, I don't know, a priori, we decided to do 3 comparisons, we can do it, it's fine. This post hoc, we're restricted. We can only use it post hoc across 3 groups only, with an overall statistically significant ANOVA. So the ANOVA has to be significant. Otherwise, we can't do the post hoc test, okay? The reason why is because this is the most powerful test and it easily detects differences to the fact that it's known as the most liberal test, okay? That's an issue because if we did more than 5 tests, or we did tests when the ANOVA wasn't significant, at that point, it's very obvious that we're just fishing for results. And if we do way more, and if, like, once again, there is no kind of safeguard, okay? The only safeguard is that we're only allowed to use this test if we have 3 groups only. If someone was to use this test on 10 groups, the chance of getting a type 1 error would be very high because of how liberal or how powerful this test is, okay? It easily detects differences. Now, Tukey's HSD is the second most powerful post-hoc test, and it's usually used when we have more than 3 treatments, okay? So, what's it called? Fisher was, 3 tests. Tukey is more than 3. And the thing it does is that it controls the family-wise error rate. So it does something to decrease the risk of getting a type 1 error, even after doing so much more comparisons, okay? Now, there's another test that's mentioned here. It's very short. It's the Games-Howell test. It's literally the exact same as Tukey, but the Tukey's test assumes that there's equal variances between the groups. The Games-Howell test does not assume equal variances, okay? That's all you have to know. So if he asks you what test doesn't assume equal variances or is like similar to Tukey, it's Games-Howell, okay? Tukey's is used when there's more than 3 treatments. It's the second most powerful and it controls the family-wise error rate. Last but not least, we have the Bonferroni test. And this one's very simple to understand. We literally just divide the significance level by the number of tests we run. So if our significance level is a p-value of 0.05 and we did 5 tests, we're going to do 0.05 divided by 5, and we're going to get a new significance level of 0.01. Okay, so every test from now on is going to follow this new significance level of 0.01. So we, don't fall into the pit hole of getting a type 1 error. So if we had many comparisons, okay, more than 6, for example, or even millions, okay, in like genomic complexes or whatever, I don't know, genomic studies, I don't know, where they have millions of genes to differentiate, we can use something known as FDR or Q values. And he didn't elaborate on these at all. I have not seen on these on past at all. I did not see them asked anywhere. But, just memorize that, anything more than 6, or if he mentions even millions, FDR and Q values are the way to go. Okay? So now we're moving on to correlation analysis. Correlation analysis will hopefully be nicer, inshallah. So we use correlation analysis to see the association between two continuous variables. So very simply, height versus weight. Okay, they're both continuous. Someone's height could be 180. Their weight could be like 150 kilograms, whatever you guys want to think. And we can see whether there's an association between the person's height and their weight. Usually we say that people who are taller have a higher weight. So let's see. So we can mainly visualize these using, these two variables as a linear relationship on a straight line on a graph like this. And the equation for that is just y equals mx plus b, as you know from high school. M being the slope, b being the y-axis thing, like where it starts at the y-axis. Not really has been asked much, but linear relationship is a possible thing. The main focus we're going to see is scatter plots, and this is what we mainly use. You can see that, the values are all over the place, kind of scattered, but you can still see some sort of an association. You can see that it's going downwards as the percentage of people, who are immunized increases, okay? So there is some kind of an association you can see on a scatter plot. And we will talk about that later. But let's say we're trying to compare between two categorical variables, someone who, someone's gender and their smoking status. So a male and smoking status of yes, for example. In this case, they're not continuous variables. So we're going to use something known as the chi-square test, okay? You guys don't really need to know about it, like any of its details. It's just literally an exam question. And two categorical variables, for example, gender and smoking status. What do we use? We use the chi-square test. Tamam? That's all you need to know. Now, I was saying that there was a relationship right here. There's a downward relationship. But how do we actually quantify the strength of a relationship if it's in a cluster? It's all messed up, right? Luckily for us, we have Pearson's R. Pearson's R is a parametric, okay? It's parametric, meaning it assumes a normal distribution in the population, okay? So there's also non-parametric tests which don't assume a normal distribution in the population. We're going to talk about a test like that later. But Pearson is parametric and it assumes a normal distribution in the population. It has no units of measurements and it's between -1 to 1. Okay? Tamam? -1 to 1. Yeah, whatever. So a positive value, like 1, for example, means that when one increases, the other increases. It's a positive correlation. But -1, for example, means that when one increases, the other decreases. And I'm going to show you guys that on a picture. Over here, we have a positive R equals 1, which is a positive correlation. As method and height increases, weight increases, okay? Positively. But this is a negative correlation, which is R -1. For example, if height increased, weight would decrease. That would be a negative correlation, and it would be stated by R -1, okay? Now, if there's no correlation at all, okay, we use R equals 0, okay? So there's no correlation and the line is just like flat like this. No correlation at all, tamam? Now we can also, quantify the strength of the relationship. So if we have an R from 0 to 0.3, it's weak, okay? This also applies to negative values, by the way. So 0 to -0.3, it's weak. In this case, since it's positive, it would be a weak, what's called weak positive correlation. If it's from 0.4 to 0.7, it's a moderate positive correlation. If it's 0.8 to 1, it's a strong correlation. Now, all of this applies to negative as well. We're just using positive numbers to make it easier, okay? So how do we calculate Pearson's R? Now, disclaimer, I'm not going to explain this because I've never seen it asked at all. I've never seen a single question on it. And it is crazy for the doctor to even think of bringing a question on this. I don't think he will. It just wastes too much time. But this is the equation. If he were to bring it to you on the final, he would bring it on the exam paper as an equation. He does not expect you guys to memorize this, definitely. And if you guys do want me to explain this, I can maybe, but it's like for now, I just won't really touch it. What you guys do have to know is that this is just sum, okay? This just means the sum of. And what you're going to do is if he gives you a bunch of variables like X and Y, let's say height and weight, and he gives you a bunch of values like 2, 3, 4, 5, or whatever, for example, you're going to have to calculate the mean of the X and the Y variable. Okay, so you're going to calculate the mean from all the numbers. So you're going to get the Y, the mean of Y, the mean of X, and then you're going to go through each individual number. So for example, you're going to plug in 2 here, okay, XI. and then you're going to plug in the mean of X, and then you're going to multiply it by, you plug in 3 over here, and then you find the mean of Y, you multiply it, and then you move down the line, and you keep adding and adding and adding, okay? And you add them together. And then you divide that by all of this down here, which is the same concept, except there's a square root instead of, multiplying these together. I'm not really going to explain this. Apologies if you guys were expecting me to, but I can assure you guys like 99.999% this is not coming on your exam, okay? Trust me. If you guys do want me to explain it, I can later. You'll never see this on past papers. He does explain how to calculate it on his slides, but you'll notice that it's like so much calculations, which is why he's probably not bringing it on the exam. So the limitation of Pearson's R is that it can't accurately represent nonlinear relationships. It's also greatly affected by outliers. You cannot extrapolate beyond the observed ranges, and you cannot establish a causation. Okay, you can establish a correlation, but not causation. So the limitations are as such. For example, if you have an association like this, the Pearson's R will not help you. The value will not help you at all, okay? It only helps in linear values, okay? So like this, for example. For something like this, or like this, for example, Pearson's R will not help you. Aside from that, it's greatly affected by outliers, okay? So if you have a scatter plot, you're going fine, but then suddenly the values just mess up and it's weird, and then it continues like normal. These outliers right here are going to affect the value or the Pearson's R completely. It's going to ruin everything, okay? And these outliers are the reason why we use the Spearman, which I'll talk about later. Another thing is that, what's it called? What was I going to say? Oh yeah, sorry. You cannot extrapolate beyond the observed ranges. So if you check out heights from 160 to 180, for example, you're only allowed to say that there's a positive correlation, and this is weight. You're only allowed to say that there's a positive correlation between height and weight from 160 to 180. Nothing else. You can't say that, for 190, for example, there's also going to be a high weight. If you go less than 160, there's going to be a low weight. You can only use the values you studied. If you go 160 to 180, you can't extrapolate beyond that. Because you never know. Maybe after 180, for example, suddenly it starts going crazy. You have no idea, okay? You can't tell unless you actually, do the study. Last but not least, you cannot, assume causation. So if this is height, okay, and this is weight, you cannot say that increased height causes increased weight. You cannot say that increased weight causes increased height. You can say that they're correlated, but you cannot say that one causes the other, okay? For that, you'd have to do like a randomized control trial or something, which we will get to later on in this crash course. Okay, so those are the limitations. Now, Spearman's R is non-parametric, okay, meaning it does not assume normal distribution. We said that Pearson is parametric. Spearman's is different because it's non-parametric, right? Now, Spearman is used for non-normal, continuous, or ordinal data. So because it's a non-parametric test, we use non-normal, continuous, or ordinal data. Ordinal data, what I mean by that is ranks. So this reduces the outlier effect. For example, you have X, which is height, Y, which is weight, for example. You have 160, 75, you have 180, 90 weight, whatever. But then you get to a height of 190, and this guy just, for some reason, he's fat. Okay, he has a weight of 170, for example. This is an outlier, okay? Or you have a guy who's like 200, height of 200, and he's a stick. He has a weight of 60, okay? Or let's say even less, 50. Okay, these are outliers, okay? Now, let me remove this to decrease confusion. But the way we decrease outliers in Spearman's test is by ranking them. So this would be number 1. This would be number 2. This would be number 3. And by ranking them like this, we decrease the effect of outliers. And what's it called? We don't affect, the overall correlation, okay? So that's the whole point of Spearman's, okay? Now, that's all you guys need to know about Spearman's, I believe. We're done. We're moving on to sampling theory. Sampling theory, I think, is a new lecture. So focus up. This one just has a bunch of definitions you have to memorize. So first off, as you guys know, samples must be randomly chosen, obviously, okay? If they're not randomly chosen, if we're just selecting ala mazajna, we might end up with a sample like this, which cannot be inferred, okay? It's not a representative sample of the population. Samples also must be sufficiently large, okay? They must be large enough for them to actually be able to represent the population, okay? Now, a census is a government survey, okay? So it eliminates the possibility that we take a sample that's not representative of the population. So the government goes around all households, tells us exactly how much males there are in the population, how much females there are in the population, what's the age ranges. This allows us to take samples that actually represent the population and, don't exclude people, okay? That's what the census is. That's what its purpose is. It's just a government survey that kind of takes, all of the demographics of the population. Now, sampling units are the individuals we sample, okay? Students, patients. For example, if we're studying blood pressure in Al-Faisal medical students from year 1 to 5, our sampling unit is Al-Faisal medical students from year 1 to 5, okay? That's pretty much it. Now, our target population is the group we want to generalize to, okay? So, مثلا, if we're talking about Al-Faisal medical students, the population that we're trying to generalize to is Al-Faisal medical students, okay? That's who we want our sample to, generalize to, okay? Now, the study or the accessible population is the part of the group we can actually reach, okay? So مثلا, maybe it's hard for us to reach different parts of the population. So the accessible people or the study, the accessible people are known as the study or accessible population, okay? Now, a sampling frame is a complete list of all members of the population you intend to study. So a hospital electronic medical record can list all patients with a specific disease, cancer, or anything of the sort. So مثلا, if you have like a list, of patients in a hospital, and it shows all, patients in the nation or all patients in the hospital who have type 2 diabetes, for example. That's a sampling frame, okay? And if your population you intend to study is type 2 diabetes, that is a sampling frame that can help you, get to those people and, actually study them, okay? Now we have two types of sampling. We have random sampling, in which everyone has an equal chance of being selected. And then we have convenience sampling, which is selecting whoever is easiest to reach, okay? And most of the time, especially with all of these, cross-sectional studies that we do in uni, it's usually convenience sampling because we're just selecting whoever's easiest to reach. It's very hard to have, a truly random chance of, selecting people for research. You know what I'm saying? Talking makes me so thirsty. So obviously, if we're doing convenience sampling, or even if we're doing random sampling, we can end up with sampling errors, okay? There are sampling errors that occur by chance. So the sample might just not represent the population by luck. So maybe by luck, remember the earlier example, maybe by luck we end up taking a sample that's full of just black spikes and we miss out the smiley people and all the others. Maybe that can happen by chance. But maybe there's a systemic or a systematic error where the study method consistently distorts the results, okay? Either by poor measurements or tools, and these cause bias, okay? And bias, we have a bunch of types. We have selection bias, we have non-responder bias, we have recall bias, okay? You guys have to remember all of these. But they're very easy, by the way. Selection bias is just the systematic exclusion of certain population members. So very simply, let's say we're studying Faisal medical students, but we only choose males. So we're basically excluding the females from the study. And maybe if we're trying to estimate attendance, for example, females maybe attend more than males. So we're basically, this is a huge bias. We're not really, looking at attendance of Faisal medical students. We're looking at attendance of Faisal male medical students, okay? If we want to do all medical students, we'd have to also look at the females and not exclude them, okay? So the solution to this is just using randomization. So randomization helps us a lot. If we just choose randomly, we won't have any selection bias, okay? Now, non-responder bias is that when non-respondents actually differ systematically from the respondents. So let's say you're giving people, a survey on activity or whatever, and the survey specifically asks, how active you are, whatever, blah, blah, blah. It's less likely that a person who isn't active is going to fill up the form. So a guy who sits at home all the time or whatever, he might be less inclined to fill the form because maybe he just doesn't feel good about it. He just doesn't want to talk about it. While people who are actually active want to brag about it, want to actually say that, yes, I'm an active person. So they'll fill out the form more, resulting in a discrepancy. There's going to be more people who are active filling the form, overinflating the values of people who are actually active, okay? So that's that. So recall bias is something when, basically if you're talking to a patient about events that happened in the past, okay, and the patient has a disease that, affect the subject's memory, okay? So maybe you have a patient with schizophrenia, patient with Alzheimer's, and you're asking about prior disease, prior, exposure, prior events or something. The patient won't remember 10 years back or 5 years back, okay? So because of this, he might give you false information, he might make up stuff. This results in bias once again, okay? And the prevention is to use medical records. So obviously now we have electronic records that, keep memory of everything, okay? Or we shorten the recall period. Maybe this guy can only remember up to 1 month. So we decrease it from 2 years to 1 month. Just remember what happened in the last month. مثلا, okay? Now, this is mainly an issue in retrospective studies where we're looking at the past. I'm going to talk about retrospective studies later. Now, what are some sampling techniques that can actually help reduce bias? Well, first off, there's two types. We have non-probability sampling. So there's selected by judgment or convenience. Okay, the selection chance is unknown. Okay, or we have probability sampling. Now, probability sampling is when patients are selected randomly or like people are selected randomly and the selection chance is actually known. Okay, we'll talk about these right now. So in random sampling, we have first off, simple random sampling. So sample units are selected independently and randomly without replacements. So مثلا you have 1,000 patients and you want to make a sample of مثلا 100, okay? So the probability supposedly for choosing these 100 people should be the sample size divided by the population size. So we end up with 1/10. So there's a 10% chance. So yeah, each sample unit has an equal chance. The probability is sample size divided by population size, okay? So in our example, 10%, okay? And the way you do this is usually with a machine that randomly selects people with a random number generator or whatever, stuff like that, tamam? Now, systematic random sampling, on the other hand, is the process of selecting study elements from an ordered sampling frame. So let's say you take a sampling frame, okay, from patients, like the registry of cancer or whatever, and the way we do this is we select people based on a pattern, okay? So to do this, we calculate the interval. So let's say we have, once again, 1,000 patients in this registry, and we want a sample of 100. This time, instead of 100 divided by 1,000, it's going to be 1,000 divided by 100, which results in 10. Okay, so we get the answer of 10. So our interval here is going to be 10. Okay, so this gives us k, which is our interval. So now we're going to randomly pick a number from between 1 and k. Let's say we land on 6. Tamam? So now the random number is 6. And from 6, we're going to select every 10th unit or kth unit, okay, until the sample is complete. So we're going to go 6, 16, 26, 36, 46, until we get 100 people. Okay, that's how systematic random sampling works. Now, the thing is, the issue with this is that although it's easier than simple random sampling because you only need one, random number, and it's also, that the samples are evenly spaced, you might miss a repeating pattern, okay, in the sampling, what's it called? In the, what's it known? The sampling frame. You might miss a pattern, okay? So let's say you have a sampling frame of patients, and by chance, it just follows this cycle of male, female, male, female, male, female. And the sampling, the systematic, what's it called? The systematic sampling method basically makes us choose only the males because we're going in order, okay? And this sampling frame follows this order. We end up missing out on all the females once again. Okay, so if there's some kind of repeating pattern that matches our interval, we may over or underrepresent people. Okay, this is known as periodicity bias. Okay, remember periodicity bias. Tamam? This is an issue that can come along in systematic random sampling. Tamam? And once again, remember that it is easier than simple random sampling. You only need one random start. And the samples in this case are evenly spaced instead of completely random. Okay? Stratified random sampling, on the other hand, is we divide the population into homogeneous subgroups known as strata. So for example, we take a patient, we divide them by age. So these are different strata, 1 to 5, that's a strata. Then we do, 6 to 7, and then we do, 8 to 10, and so on and so forth. These are strata, and what's it called? These strata are what we divide people into, and the rules are that each member belongs to only one stratum, and all members are included in the stratum. So no one can have more than one stratum or one group, and all members or all people in the population have to be in a stratum. You can't have someone outside of a stratum, okay? Last but not least, I think for random sampling, there's cluster random sampling, used when populations naturally form groups, okay? So مثلا, if you're looking at diabetic patients all around the kingdom, all of them naturally fall into different hospitals, okay? Different clinics, okay? Or people fall into different families, for example. And there's different types of cluster random sampling. There's 1-stage and 2-stage. So let's say we're looking at people with diabetes, and we know that there's 100 hospitals. So from these 100 hospitals, we randomly select 10, and then we look at all diabetic patients in these 10 hospitals. Tamam? So all people with diabetes. Now, but 2-stage is we randomly select select clusters. So let's say we select 10 hospitals again. Then we sample members within each cluster. So we specifically pick and choose مثلا 5 diabetic patients randomly in this cluster. Tamam? That's how cluster random sampling works. Now, for non-random methods, we have, first off, there's pros for it. Non-random methods are easy, fast, inexpensive, can be done quickly. But the issue with them is that they're prone to bias and they're less representative. Okay, they're not representative of the population usually. They're actually very prone to bias based on how you do them. It's not recommended usually. Proper studies are always randomized. Okay, but for us to know, convenience sampling. So this is non-random, and it's literally just us Al-Faisal students when we send links on the WhatsApp group chat. Okay, our sample is chosen from easy to reach participants. Method and surveying students at the food court, going around with a QR code telling people to sign it. Okay. Selecting patients from a clinic. A patient comes in and I tell him to sign my QR code or something. Scan my QR code. Or just choosing classmates with any mini law. That's all convenience sampling. It's very easy, but as you can tell, it is not representative of the population at all. You can very easily end up with skewed data or whatever. Okay. Now, snowball sampling, on the other hand, is also another non-random method, and it's literally like a snowball. The reason why is it's like a Ponzi scheme where participants recruit friends or contacts, okay? So let's say you have Alcoholics Anonymous or something, okay? You're studying alcoholic patients or people with rare diseases, okay? Usually people who are drug users, they know other drug users, okay? So what we do is we tell the first participant who's a drug user, for example, an alcoholic, to refer other alcoholics, okay? And then those alcoholics will refer other alcoholics, and then it's going to be a huge circle or a snowball of people recruiting each other to, what's it called? Do the study, okay? Participate in the study. Obviously, compliance is probably an issue with this, but this is all he wants you guys to know. This is snowball sampling, okay? Next up, the last 2 lectures, principle of epidemiology. I'm actually about to lose my mind. I think I'm doing good on time, which is not bad at all. So let's keep going, I guess. So these lectures also changed a bit from last year, but luckily I have the slides this time around. So epidemiology, it's a data-driven study. Data-driven is very important, okay? It's a study of the distribution and determinants of health-related states or events in specified populations, okay? And the application of all of this knowledge to control the health problems. That's what epidemiology is. Just memorize this definition, okay? Now, the frequency, when we talk about epidemiology, it's the number of health events relative to the population size. So this enables comparison. So the frequency, because it's relative to population size, we can compare countries with huge population sizes to countries with low population sizes, and we can still look at the frequency of health events, okay? We can compare between countries. Now, pattern is this was literally a question in our exam. It just asked, what is pattern? Pattern is time, place, and person. So it's literally how health events occur by time, place, and person. What's the pattern of these health events happening, okay? Now, determinants are the causes and factors that influence the occurrence of health-related events. So we can use epidemiology to propose interventions for disease prevention. So if we figure out the determinants, we figure out the causes and factors, we can then, give out interventions, we can give out, awareness to prevent this disease. Okay, that's the whole point of epidemiology. The objectives are to identify the causes of disease and risk factors, determine disease burden in the community, so how bad this disease is affecting the community, look at the natural history of how it progresses, and then see the prognosis, whether it's bad or good. So if patients recover well or they die, and then last but not least, develop public health policy. So policies that help avoid all of these health crises. Okay. Now interventions can be population-based approach, which is just media. So like awareness events, whatever. Giving people awareness method or giving advertisements on smoking or something. Okay, that's population-based. The high-risk approach is expensive because it's specifically targeted only to people who are at high risk of some kind of health event. Okay, some sort of disease. Okay, so that's why it's high risk. Okay. And now disease, I don't know why they're teaching you guys this, these lectures actually piss me off. It results from the interaction of a host, okay, and an agent. So the host is us, the agent is the bacteria, for example, and the environment is the air we breathe, okay, the pollution, for example. For, you guys remember microbiology, a vector may be involved, like a mosquito passing on malaria or something. Now, most diseases, regardless, they always involve genetic, behavioral, and environmental factors. So maybe you have a genetic predisposition to some sort of disease, but it won't get activated unless you're in the right environmental or behavioral, what's it called, environment, okay, or factors, sorry. But all of these, play different kind of roles depending on the disease, okay? Genetic, behavioral, and environmental factors. They all play a role in disease. Now we're going to talk about some people. We have John Snow. He's the father of epidemiology. He believed that cholera could spread through water. Crazy. Turns out he was right. He mapped cholera deaths throughout wherever he lived, and he noticed that more people were dying near the water, okay? Wherever there was wells, I believe, or wells or pumps, water pumps. So because of this, he was able to ascertain the cause of infection, and because of this, he's kicked off epidemiology, the study of disease and whatnot. He was able to figure out that cholera spread through water, which is really cool. So John Snow, once again, by the way, I know I'm explaining a lot, but when it comes to these questions, like genuinely on the exam, I remember she asked us who is associated with cholera, and the answer was John Snow. It was that easy. So just remember cholera with John Snow, okay? I don't know if it's going to get repeated, but that's besides the point. Tamam? Edward Jenner, you might get Edward Jenner. Edward Jenner, he noticed that people who were exposed to cowpox did not get smallpox, and he injected people with cowpox to prevent smallpox. Sounds familiar? It's a vaccine. So he created the first vaccines, okay? Edward Jenner created the first vaccines. Remember that, okay? That's all you need to know, okay? He's related to cowpox and smallpox as well. I don't know. Now we're going to talk about all the different types of studies. This is literally Aspire for those who took Aspire. We're going to be talking about cohorts, ecological, cross-sectional, case control studies. All of these are observational. The reason they're observational is because, there's no intervention, tamam? So the researcher who's researching, he observes the exposure and he looks at the outcome and he makes observation. That's it. And he can do it over time or at once, depends on the type of study. And we're going to talk about all of them right now. So first off, we have ecological studies. Ecological studies, it looks at groups. It doesn't look at individuals. So for example, countries. The unit of analysis is usually a population, a country, a school, a city, whatever you want. And you can see here, this graph is saying that countries that eat more chocolate have more Nobel laureates, okay? And you can see that there's a positive association. That's kind of funny. But there's an issue with this. The issue is that individuals are assumed to have the average exposure outcome of their group, okay? But that's wrong. We may wrongly attribute a group trend to individuals, okay? This is known as the ecologic fallacy. Where's my pen? Ecologic fallacy. So please don't make this mistake. For example, Switzerland here, you can't, say that, oh, you're Switzerland, you must eat a lot of chocolate, therefore you must be a Nobel laureate, okay? It doesn't make sense. You can't, associate, you can't, like we said, with all of these, associations, we can't, figure out causation, okay? Eating a lot of chocolate doesn't mean they're Nobel laureates. And because this is an ecologic study, a lot of the time the individual might not, like an individual in Switzerland might not even eat chocolate at all. So because of this, even though his country eats a lot of chocolate, it would be wrong for you to say that you eat a lot of chocolate because your country eats a lot of chocolate in general, okay? Does that make sense? I hope that makes sense. Now, cross-sectional studies, they measure exposure and disease at the same time. It's basically a snapshot in time. For example, if we check a person's cholesterol level and then an ECG and look for chronic heart disease, okay? And we do this all at once. And this identifies prevalent cases that already exist, okay? But it doesn't look at new ones. For example, it doesn't look at disease that's, happening over time. It doesn't look at incidence, okay? That's another concept. It only looks at disease that's, currently, like right now, you have a disease right now. It doesn't look at any new ones or any upcoming ones. It's just a snapshot in time that tells you how much people have the disease right now. Tamam? Cross-sectional studies are actually, they have a lot of issues with them. First off, temporal bias. Since you're measuring exposure and disease at the same time, you cannot tell which came first. So you cannot, extrapolate causation. So you cannot say, oh, For example, you cannot say that, although it's obvious to us because there are other studies, we cannot say that increased cholesterol causes chronic heart disease. Because we took it at the same time, we could say, chronic heart disease causes increased cholesterol. Both ways go because it's a cross-sectional study. So this is the temporal bias, okay? We cannot tell which came first. We cannot extrapolate causation. Survival bias, on the other hand, is caused because, there might be people who die early, okay, before the cross-sectional studies happens, okay? So people who live long enough with the disease are included, but early deaths are missed. So the results may be misleading. Maybe people who had more severe disease might not be able to be part of the cross-sectional study, so you're missing out on some data, okay? So the results may be misleading. Last but not least is self-report issues. Because cross-sectional studies are usually, cross-sectional studies are the one we do on, with forms. We go around telling people to fill out my form. What's it called? Common variables like height or weight or age, they may be, misreported, underreported, overreported. There's a lot of recall bias, okay? Recall bias. That's the issue with cross-sectional studies. Next up, we have case control studies. Now, case control studies, we basically look at people who have the disease. This is known as the case. Then we look at people who do not have the disease, okay? This is, our reference group, tamam? And then we look at if they were exposed to something or not. So let's say the case is lung cancer. Lung cancer. The exposure is smoking, okay? So realistically, because we know smoking causes lung cancer, this case control study is going to show us that people who have the disease have more exposure to smoking than people who do not have the disease. That's a case control study. Tamam? Now, in case controls, we can do something known as matching. So it's selecting controls to be similar to the cases. So let's say 25% of the people with lung cancer are married. So we're going to make sure that our control group also has a level of like 25% of people who are married as well. Now, that's more general. That's looking at the whole group as a whole. But individual matching is when we look at each case, each person with lung cancer. In the method, we find a guy who's 25 years old, married, he has lung cancer. We try and find a guy without lung cancer who's also 25 and married and has the same, who looks very similar or very similar to the guy with lung cancer. We're matching each individual, okay? This is very specific, okay? Now, that's it for case control studies. Now, cohort studies, instead of looking at cases, instead of finding people with disease, we're actually selecting people who are exposed to something or not exposed to something and following them over time. And we have a group of people. This guy is exposed to smoking. This guy isn't exposed to smoking. Let's see if he gets lung cancer at some point. Okay? So we compare disease incidence between the two groups. And if there's a positive association, there should be a higher rate of disease in the people who have been exposed to smoke. Have been exposed to the exposure. Kind of funny. Now, the pros of the population-based cohort is that you can study multiple exposures simultaneously. So you can study smoking, you can study cholesterol, all at once. You can see whether or not, it's a risk factor for specific diseases. Tamam? Now, this is how it looks like. We have a defined population. We see people who are exposed, not exposed, and then we see if they get the disease or not. Okay, we follow up. Tamam? So there's two types of cohort studies. We have prospective. So prospective is right now, method in 2025, I find people who have, who are smoking and people who aren't smoking. And then I follow up with them over 20 years to see who develops lung cancer and who doesn't. So prospective cohort studies, they have the disadvantage of time, okay? A lot of researchers aren't interested in spending 20 years researching, okay? Retrospective cohorts, on the other hand, is if we have data, for example, in the hospital, we look at the past. Method, I go back to the records of 2000 of patients who came in 2000, look at whether or not they smoke or not, and then I look at the records of 2025 currently, see how much of them have lung cancer and how much don't. That's known as a retrospective. So I'm looking at the past, okay? I'm not really, following up with them in the future. It's just that I looked at the records from 2000 and then saw if they developed the disease anytime in the future. That's a retrospective, tamam? I hope that makes sense. Now, last but not least, the gold standard in medicine, the randomized clinical trial, okay? Randomized trials, they evaluate efficacy or side effects of interventions, okay? They're controlled experiments. So method, if we want to test the efficacy of a new drug, we want to see treatments, we want to evaluate screening or prevention or even healthcare programs, we do randomized trials. They're randomized, okay? And they're controlled. So for example, we have a treatment and we have a new one. Okay, so new treatment, old treatment. We give some people the new treatment, we give some people the current treatment, and we see if there's a difference between them. If there's a difference between them and it's a good difference, that's when people start switching to the new treatment. Okay. So there's two ways to do the randomized trials. So funnily enough, there's without randomization. So a randomized trial where you allocate subjects without randomization. I don't think that makes sense, but it's okay. So we have two types of that. We have without comparison. So method a case study or case series. So in a case study or a case series, there's no control group. We just give people the new drug and report what happens. Okay, but we're not comparing methadone to the old drug. Now with comparison, we're either looking at historical controls, we're looking at how the old drug used to work in the past compared to the new therapy currently. Okay, so if we have a new drug, we look at another article or systematic review in the past which told us the differences in people who took the old drug, and we compare it to the new drug that we're giving to patients now. There's also a non-randomized control where we assign patients based on factors like admission day. So Sunday into you're getting the new drug. Monday you're getting the old drug. Tuesday you're getting the new drug. Wednesday you're getting the old drug. Something like that. Okay. All of it, Salah, since it's not randomized, it results in bias, mistakes. It's kind of useless. That's why randomization and blinding is the best. Randomization, we assign patients unpredictably, usually done by a computer. It's like doing any mini, miny, mo, or a coin toss. The purpose is to prevent selection bias and ensure comparable groups, obviously. Now, placebo is an inert substance that mimics the therapy, okay? So hatta in these randomized trials, we give people placebo so they don't, they don't know what's happening to them. Methadone, the patient who's given nothing, for example, might not improve, but maybe the new drug, okay, is given to the patient, he improves, but the patient is also given a placebo, and the placebo causes the patient to also feel better. So we want to make sure the new drug isn't, the same as a placebo. We want to make sure it's better than a placebo, okay, that there's an actual difference. Now, double blinding is when both the participants, I explained this earlier, study personnel are unaware of group assignments to reduce bias. So methadone, the person giving the drug to the patient doesn't know what drug it is. The patient doesn't know what drug it is. Both the placebo and the drug itself literally are designed to smell the same, look the same. They're literally the same. There's no way to tell the difference between them. And that's what a double-blind study is. Tamam? Last but not least, we have epidemiology too. So as we know, oh my God. Okay. So there are screening tests. There are tests to test people for disease. Okay. And we have this table showing us, what outcomes can happen. We can have either the disease is present, okay, and the test is positive. This is known as a true positive. So the sick person has been correctly identified. Mumtaz. But what if the disease is absent, but the test still comes out as positive? That's an issue. That's a false positive. The healthy person is incorrectly labeled as positive. Same thing with negative tests. If the disease is present, but the test is negative, that's an issue. You just missed a sick person. And if the disease is absent, but the test is negative, you made a good issue. He made a good choice. Yeah, the test worked. It correctly identified a healthy person. Tamam? So screening tests detect disease in asymptomatic people. So for example, prostate cancer, it's usually asymptomatic for a long time, but screening tests can detect prostate cancer to the point that we've done so much prostate cancer screening tests that it's actually become a hindrance. Because prostate cancer, people usually don't notice it until later on in life anyways. So why would you bother the patient with it so early on? Diagnostic tests confirm disease in symptomatic patients. So a patient coming in with a headache or something, you do an MRI and find a brain tumor. Okay, that's a diagnostic test. It's confirming the disease. Now, the sensitivity of a test is the ability of a test to detect disease when it's really there. So the equation for it is true positives divided by true positives plus false negatives. So for example, let's say we have 100 people. Let's say 100 of them are sick. They have the disease. This test, okay, marks 80% of them as sick, and 20% of them as or 20 of them as what's it called? Not sick. Tamam? So if I'm correct, once again, it's 100, 80, 20. We're going to divide 80 by 100 because it's what's it called? This is true positive. This is false negative. Okay, so true positive plus false negative is 100. So the sensitivity of this test is 80%. Okay, it's fine, it's okay, but it's not the best. Okay, so this 80% of the time, this test will be able to detect a patient who has the disease, and we're trying to limit the false negatives as much as possible. Okay. Specificity, on the other hand, is the ability of a test to exclude disease when it's not there. So it's the what's it called? The equation is true negatives divided by true negatives plus false positives. So let's say we have, once again, 100 healthy people, okay? In this case, 80%, or sorry, let's say for example, 90% of people who test negative, okay? So these are true negatives. 10%, on the other hand, become false positives, okay? The test is positive, but they don't have the disease. So the way we, calculate this is true negatives divided by true negatives plus false positives, which is 100. So the specificity of this test is 90%. Tamam? And this test tries specificity. The idea of specificity is that we want to try and limit the amount of false positives as much as possible. We want it to be specific to the disease. Okay. For example, I think you guys are taking lupus and MSI. One of the antibodies that are specific for lupus is anti-Smith antibodies, anti-dsDNA. Anti-Smith antibodies are specific to lupus. So if you see them, you're like, okay, I know this is lupus. You know what I'm saying? So that's specificity. Okay. ANA, on the other hand, anti-nuclear antibodies, it's found in almost any autoimmune disease. Okay. So it's not specific, but at the very least, if a patient comes with, some kind of autoimmune disease, you can be very sure that the ANA will be elevated. Okay. That's just examples. Tamam? Now, positive predictive value, I'm not going to do explanations, khalas. Or like I'm not going to do the blackboard. It's the probability that someone with a positive result actually has the disease, okay? So this is true positives divided by true positives plus false positives. So if we have, looks like I'm going to do the blackboard thing anyways, but khalas, if we have 100 patients, okay? Let's say we have, let's say we have 90 sick patients, 90, they're sick, 10 normal patients, okay? So out of this, we get let's say we get 70 true positives, and over here we get 5 false positives. So it's going to be 70 divided by 75. Okay, because you got 70 true positives, but you got 70 true positives plus 5 false positives in the denominator. So 70 divided by 75 is actually, I don't know, 70 divided by 75, 0.93, so 93%. So the positive predictive value of this test is 93%. You're mostly going to get positive results with people who actually have the disease. Negative predictive value is the probability that someone with a negative result doesn't have the disease. Okay, so you have true negatives divided by true negatives plus false negatives. The same concept. So if you have, let's say you have 90 healthy patients and you have 10 sick patients. Okay, 5 of these people turned out to be negative. 80% of these people turned out to be negative. So you have 80 true negatives. Okay, these are true negatives. Let me explain this properly. You have 80 true negatives and then 5 false negatives. Tamam? So 80 true negatives, and then what's it called? You do 80 plus 5. So it's 80 divided by 85. In this case, I don't know, what is it? 94%. Okay. So the negative predictive value of this test is 94%. So you're sure that if a patient is, negative, he most likely doesn't have the disease. Okay. I hope that makes sense. Now, predictive value, something very important to know is that it depends on the prevalence of the disease. Okay. So even if we have a super good test, diseases that aren't super common may have a low positive predictive value. Okay. So a very rare disease, even though we have the perfect test, it might not just show up as it might have a low PPV anyways. Okay. Now, sensitivity and specificity is actually a balancing act. So let's say you're like, okay, why can't I increase the sensitivity of the test? Because you're going to decrease specificity. Okay. Both of them are related, and I'm going to show you guys why on the ROC curve. But generally, it's a balancing act. You want to try and find the highest sensitivity with the highest specificity. A way people go around this is by doing screening tests and confirmatory tests. Screening tests are made to prioritize sensitivity. They catch every possible case. So for example, ANA. ANA would be our screening test, anti-nuclear antibodies. Our confirmatory test, which is the anti-Smith antibody, is specific to lupus. So it avoids false positive. It's a confirmatory test. It's not sensitive because you won't see it in every patient with lupus, but every patient with lupus will probably have anti-Smith. Does that make sense? So that's the difference between specific and sensitivity. I'm going to show you guys over here. Now I kind of tried to run this through a upscaler through AI, so it kind of looks messed up. I'll explain the idea anyway. So back in the days, we don't do this anymore, by the way. ELISA and Western blot, okay? So for HIV, we used to screen people with ELISA. And if it turned out positive, the patient isn't confirmed HIV positive. It's still a question mark, okay? What we actually need to do is do a Western blot right after. And once the Western blot comes out positive, that's when we're like, okay, 100% this patient has HIV, okay? I hope that makes sense. So that's a screening and confirmatory test. So what is the ROC curve I talked about earlier? The ROC curve is a receiver operating characteristic, and it's basically a tool that shows us the test's performance across all possible cutoff values. So if I wanted to, see what the test would look like at 80% sensitivity, I can also see the specificity of the test, okay? It shows me all the possible values, okay, across this graph. Now, on the y-axis, we have the sensitivity or the true positive rate. On the x-axis, we have the false positive rate, which is 1 minus specificity. This means that going rightwards on the x-axis means actually less specificity. So over here is a perfect 100% specificity. And going upwards on the x-axis means a 100% sensitivity, or higher sensitivity, sorry. Okay? Now, the way I like to think about this, or the way the doctor likes to think about it too, is that we have these two graphs. We have, let's say like this is a blood pressure, sorry, not blood pressure. Let's say this is blood glucose, okay? These are the blood glucose levels. Now, I know these are unrealistic numbers, but let's say these are the blood glucose numbers in patients who don't have the disease. Patients who are blue don't have the disease. And these are the blood glucose levels in patients who have the disease, sorry. Okay? So we can see that there's a difference. And maybe we want to make a test, to see if people have diabetes, we check their blood glucose levels, okay? Now, the issue is, this dotted line here is the cutoff point, okay? So anyone who is after this, after this point, let's say this is 60, has the disease, has diabetes, okay? We say that they have diabetes or they're positive for this test. The issue is you can see that there's this pink area here. Some people who don't have the disease still cross this line, okay? So the test isn't 100% specific, okay? You can still have false positives, okay? The test also isn't even that sensitive, to be honest, because look, all of this green line over here is people who have the disease, but we're missing them, okay? Because our dotted line is over here. Tamam? I hope that makes sense. So you're probably thinking, okay, I want to make my test more sensitive. Let me move this line back here. So if you move the line back here, the test becomes more sensitive, but guess what? The test becomes less specific. A lot of people who don't have the disease are becoming positive all of a sudden. Okay, so you're telling me, okay, Saad, let me try and increase sensitivity. So you increase sensitivity. You increase specificity by moving the line here. So now the test is more specific. People who have the disease and test positive, 100% have the disease. But look at now, all these people are being missed out on. All these people who have the disease aren't getting positive results. So that's what I mean by balancing act, okay? And we can see all of it on this these graphs here, the AUC graph, the ROC graph. We can see all of it. So if we have a good enough test that discerns between people who don't have the disease and people who have the disease, you're going to have a ROC curve that looks like this. Notice how it's very close to up here. Up here is the optimal point where the specificity is 100%. The sensitivity is almost 100% as well, okay? As we get, the graphs become closer and closer to each other, the graph starts to flatten out. It becomes like this, until it eventually becomes flat, okay? Like this, or not flat, but like basically completely flat at a slanted 0.5 angle or whatever. Now this means, if it gets to this level, this means the test does not work at all. It's no better than just choosing randomly, okay? And we're going to discuss this right now using the AUC, the area under the ROC curve. The AUC is the probability that a randomly chosen diseased person will have a higher test result than a randomly chosen healthy person. So let's say diabetes, okay? The AUC is going to tell us that, okay, any person with diabetes, this is the chance that they're going to have a higher blood glucose level or a positive result than a random healthy person, okay? If the AUC is 1%, that means there's a 100% chance and the diseased person has a higher test result. So this test works 100% of the time, okay? It's very good at discerning. So it's a good test. This is an amazing test. Look at the line, bro. It's literally over here. Okay. What's it called? But for example, if we had this, like I said, this flat line, AUC of 0.5, the chance of selecting someone who has the disease and he has a higher, glucose level than someone who doesn't have the disease is 50%. That's completely random. There's a 50% chance that the test is good. There's a 50% chance that the test is wrong. So it's no better than random chance. Okay. So we have these AUC ranges. I don't know if they expect you to memorize them. I don't know if she expects you to memorize them, but it's good to know. So 0.9 to 1 is excellent. Okay, the test is almost perfect. Okay, AUC of 0.8 to 0.89, it's useful for diagnosis. 0.7 to 0.9 is fair. But now once we get to this level, we need context. We need symptoms or some kind of disease-specific symptoms to, affirm this test. Okay, it's acceptable. Once we get to 0.6 to 0.69, it becomes poor. Once we get to 0.5, 0.5 is useless. No discrimination, random chance. So why do we do all this? It's in order to compare diagnostic tests. So we want to see if one test is better than the other. We want to find the best cutoff point, the best sensitivity and specificity for this test possible. And we want to see the sensitivity specificity trade-offs. I want to see what happens when I increase sensitivity. I want to see what happens when I decrease specificity, for example. Okay, that's the whole point of this ROC curve. And thank you so much, guys. That is it for my past session. That is basically BEP post-midterm. Hopefully everything explained. Hopefully everything you guys need for the final exam post-midterm wise, inshallah. Once again, my number is at the start of this pal. If you guys have any questions, any past papers you're looking for, let me know. And please, 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 please fill out the feedback form. I want to see if I'm doing good or not. I want to know if this was actually a good session or not. And over here, I have the Anki team's Anki. Anki team is currently working on amazing post-midterm BEP Anki. If I do end up making I do plan on making a post-midterm Anki deck. If I do end up making that, I'm going to upload that there as well. Post-midterm BEP Anki. But you're going to, if you scan this link, you're going to see all the Anki teams Anki if you want to practice BEP. And yeah, thank you guys so much for your time. Now, notice how it says question time. Right now, I'm going to spend some time answering questions just for practice, but I generally recommend you just go to the past papers and just start solving yourself, right? I'm going to solve some questions, but there's a bunch of past papers out there. So it's way better for you to solve them on your own. So if you understood everything from the PAL, thank you so much. And best of luck on your BEP final, inshallah. BEP is one of the, in my opinion, one of the greatest parallels. I enjoyed it a lot. And I genuinely hope I was able to share some of that understanding. I really like the understanding aspect of it. I hope you guys were able to understand anything. Inshallah, ya Rab. And if I was able to help you guys understand, please once again scan the feedback form. Let's start with the questions. So, very simply, guys, I don't want to take too much time. As sample size increases, a 95% confidence interval calculated from a random sample will more likely get narrower, right? So we said that if we have a higher sample size, remember that SEM is equal to this, what's it called, sigma, divided by square root of n. So if n gets bigger, the SEM decreases. Because the SEM decreases, our confidence interval gets narrower, okay? It gets smaller, okay? Method will go from this all the way to this. And that's very small, but you get the point. So it gets narrower. Come on. Next question. A researcher, no, I think this one was difficult, or at least like he could trick you guys with this. A lot of you guys might not know, be able to solve this, yeah. A researcher reports a 95% confidence interval for the population ranging from, where's my thing? 4.55 to 19.45. And the sample mean is 12. Assuming a normal distribution using the standard 95 z value, what is the standard error of the mean? Okay, so this question is not asking us to calculate the confidence interval. It actually gave us the confidence interval. It's telling us to calculate the standard error of the mean. Interesting. So how do we do this? So we know that the mean is 12, and we know that the confidence interval ranges from 4.55 to 19.45. So let me take, for example, 19.45. Tamam? Wait, let me remember this. 4.5 to 19.45. So I hope I'm correct. Tamam? And our sample mean is 12. Tamam? So we want to find out what the SEM is. So very simply, we plug it into our equation. So our equation, remember, to find the confidence interval was confidence interval equals mean, which is 12, plus and minus 1.96, because it's a 95% confidence interval, times SEM. We want to figure out what the SEM is. So luckily for us, we have the confidence interval, so we can literally replace this with anything. So to get 19.45, we obviously had to add. So I'm going to do this and put 19.45 here. Tamam? So very simply, guys, this is common algebra, basic algebra. What we're going to do first is we're going to take the 12 to the other side and minus. So it's going to become 19.45 minus 12. Tamam? That gives us 7.45. Tamam? So all of that's gone now. 7.45 equals 1.96 times SEM. So we can remove these parentheses. And to move this to the other side, we just, once again, basic algebra, divide 1.96. So 7.45 divided by 1.96 gives us 3.8. Tamam? 3.8. So if I remove this, all of this, I'll get basically 3.8 equals SEM. So if I look at the options, oh, did I reveal the answer before I started? I hope I didn't. But yeah, the answer is 3.8. Tamam? So that's how we calculate that. Now, obviously, my calculator gave me like 3.8000. In the exam, you're expected to round up or round down, depending on, what answer you get. But it'll be very close. Yeah, you just choose the closest option, basically. Tamam? So for example, even if I got 3.9, I'd still choose 3.8 because it's closer to 3.8. Tamam? Now let's say this confidence interval is 95% and it covers the null hypothesis, which is 100. But it also touches the clinically important value of 110. What do we do? First off, we collect more data, but we also know that this test is low power. Remember I said that if it touches both the null hypothesis and the clinically important value, it's low power, صح? So we obviously need to collect more data. The test is inconclusive. Tamam? Next, in a study evaluating a new screening test, the researchers set alpha to be 0.05 and beta to be 0.1. What is the statistical power of the study? What is power again? It is 1 minus beta. Beta is 0.1. So 1 minus 0.1 is 0.9. Literally, that's it. Okay? So power is 1 minus beta. And, once again, the doctor will literally give you guys the values. فَمَا عَلَيْكُمْ. It'll be very simple like this here. Clinical trial is testing a new drug, but the researchers are concerned that the study might fail to detect a true effect. Which of the following strategies would increase the statistical power of the study? So increase the sample size, decrease the effect size, increase the variability, use a less strict significance level. Okay. So technically, we could use a less strict significance level. We could increase alpha, right? It wasn't mentioned in the slides, but we don't do this. It's not practical at all. What's more practical for us as researchers is to increase the sample size, right? Decreasing the effect size wouldn't increase the power. Increasing the variability would also decrease the power. The only option we're left with is one of the options which was mentioned in the list is increasing the sample size. Tamam? So a researcher, all right, my screen's messed up. A researcher wants to evaluate the effect of a new medication on blood pressure by measuring patients before and after the treatment. Which statistical test is most appropriate for comparing the pre- and post-treatment measurements in the same group of patients? Now, because these are the same group of patients, remember, we're looking at them before and after, okay? We're looking at the differences before and after. This would be a paired t-test, okay? We're looking at the same patient before we give him the medication and after we give him the medication. So it's a paired t-test, tamam? Now, in hypothesis testing, the difference between two groups means the two groups means divided by the standard error of the difference produces which of the following statistics? So the answer is t-value. So once again, we said that the t-value is the two group means. So we said it's going to be the sample mean minus the population mean divided by the standard error of the differences, or specifically, what's it called? The standard error of, what's it called? The standard error of the sample. So once again, when we're doing t-tests, we don't know the standard deviation. we know only the standard deviation of the sample, which we use to extrapolate the SEM. Okay, so the standard error of the mean is from the sample. Okay, and it gives us the following statistic, which is the t-value. Tamam? Hope that makes sense. Now, when performing multiple statistics tests, the error of making a type 1 error increases. A common post-hoc procedure to address this is to divide the significance level by the total number of tests conducted. This is just straight recall. The answer is Bonferroni. Remember, Bonferroni is the one where we divide the significance level, so 0.05, by 5 tests, for example, to get a new significance value of 0.01. The Fisher's LSD, remember Fisher's LSD is used a priori. Okay, oops, I spelled that wrong. My handwriting sucks. Or it can be used 3 tests, only post-hoc. Tamam? 3 tests post-hoc. Tamam? I should just stop writing, to be honest. I don't think my handwriting is good. Tukey's HSD, on the other hand, is for more than 3 tests, post-hoc, and it fixes the family-wise error rate, if you guys remember that, okay? Tamam? Now, this question is talking about Bonferroni. If the null hypothesis is true, the F value, so this is talking about ANOVA, مبدئيا. F value is associated with ANOVA. And if the null hypothesis is true, the most likely F value will be 1, or anything near 1. 10 and 100 would mean the thing is rejected, the null hypothesis is rejected, so H1. 0.1 and 0, I'm actually not sure what that would mean, but just know that anything near 1 is null hypothesis is true. Anything more than 10 means that, anything more than 1 means that the null hypothesis is rejected, okay? In a study examining the association between, blood pressure and age in the Saudi population, if the correlation coefficient is 0.85, what does this suggest? Now, 0.85, first off, it's positive, right? So that means there's a positive correlation. This also is 0.85. It's very high. So that means there's a strong correlation. So we can see that the only answer that fits here is D. This suggests that as age increases, there is a high tendency for blood pressure to also increase in the Saudi population, suggested by the coefficient of 0.85. Tamam? As we get less and less, it becomes moderate to weak. I mentioned this earlier in the past session. You guys should check that out again. Oops, this one just straight up gives the answer. Okay, I'm sorry about that. When should the Pearson correlation be used instead of the Spearman correlation in statistical analysis? So Pearson, remember, is parametric, tamam? P for parametric means it assumes that there's a what's it called? The values are normally distributed, okay? Spearman, on the other hand, doesn't assume that the values are normally distributed, okay, and it's used to kind of what's it called? It's used on like non-normal values, okay? So if the variables are normally distributed, that's when we're going to use Pearson, tamam? Instead of Spearman. Spearman is non-parametric. It takes non-normal values. Okay, sorry for showing you guys the answer. I thought I fixed everything. In a population of 100 individuals, you take a systematic sample size, or you want to select a systematic sample size of n equals 5. Which of the following represents a correct example of systematic sampling? So what is systematic sampling again? So systematic sampling is when we took 100, divided it by 5 to get a k of a k of 20. So now we're going to choose a random number, 1 to 20. Let's say we choose 17, and then go from every 20th value. So we're going to do 17, 37, and then 57 until we get a sample size of 5. So which one would answer be? It would be D, where we select every 20th individual after choosing a random starting point between 1 and 20. That's a systematic sampling. A survey on depression symptoms is emailed to university students, but only 40% of people respond. Follow-up data shows that students with higher stress levels were less likely to complete the survey, and that researchers analyze only the responses they received and report the prevalence based on that sample. Which type of bias most threatens the validity of the study? Non-responder, informative, observer, sampling. The answer is non-responder. So remember, non-responder bias is when the people who answer the form are different from the people who don't answer the form. So in this example, the people who don't answer the form are the ones who have high stress levels, okay? So there's a lot of bias in this form, tamam? Now, during the early development of epidemiology, blah, 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 a guy traced a cholera outbreak You guys should know the answer just from seeing this. It's Jon Snow. Jon Snow is the guy associated with cholera. Tamam? I hope that makes sense. Researchers want to investigate whether exposure to new energy drinks is associated with the development of atrial fibrillation. So they identify 150 patients who were recently diagnosed with atrial fibrillation and compare them to 300 age-matched individuals without atrial fibrillation from the same hospitals. Then they look at the medical records and interviews to determine prior energy drink consumption. Which study design is being used? So in this study design, they are looking at people. The first thing they look at is people with the disease. Okay, and because of this, it's a case control study. It would be a cohort study if they looked at the exposure first, if they got people who drank energy drinks and people who don't drink energy drinks, and then see if they develop disease. But in this case, since they're seeing people who already have developed the disease and then looking at exposures, this is known as a case control study. So a new screening test for hepatitis B is evaluated in a group of 200 individuals, of whom 80 truly have the disease based on the gold standard. The test correctly identifies 68 of the diseased individuals, but misses the remaining 12. So these are false negatives. These are true positives. It also incorrectly labels 10 healthy individuals as positive. What is the sensitivity of the test? So to calculate it, we just do, 68, which is the true positive rate, and then add the true positive rate plus the false negative rate, which is 80. Okay, so what we end up with basically for Nihai is that the answer to this is 85. Okay, so the sensitivity of the test is 85%. Tamam? A new blood test developed to detect early kidney fibrosis. After evaluating the test on a large sample using the ROC curve, the area under the curve is 0.50. Tamam? Which of the following best describes what an AUC of 0.5 means? So what did we say about 0.5 again? 0.5 means that there's a 50% chance that the person with the disease is actually identified as having a higher test score or a positive test score more than the person who's normal, which is basically a half, a 50-50 chance. So there is no, sensitivity, or there is no, the test doesn't have any discriminative ability, and it performs no better than random guessing. So that's the answer here. Tamam? Oh my God, thank you guys so much. I finished the pal, I guess. Once again, I answered only a few questions. You guys can, ask me much more on WhatsApp. The past papers, there's a lot of them. There's a lot of questions. If you guys have any questions on post-midterm, questions, I could definitely help you guys out. I can explain them, whatever you guys would like. Once again, do the feedback. Please fill up the feedback form. I really do want to know if I did a good job because I really wanted to. And there is the Anki here for you guys to solve. If you guys want to do the Anki, it's under the Anki committee. Shout out Anki committee, Maryam and Malik. God bless them. So yeah, thank you guys so much for listening, and I really do hope this helps you guys for your post midterm. Let me know, guys. And once again, your best friend for BEP is going to be this crash course, past papers. Shout out Khalid Jamil's crash course if you want a quick summary to read through the slides. Although some of the lectures changed. And last but not least, I do recommend at least going through the slides at least once, because the doctor does mention a lot of examples in his slides, and these examples are basically what he brings on the exam. Pretty much. So make sure to do all that, and you guys will be great for the parallel, inshallah. Alaikum. Best of luck, guys. Whenever you guys are listening to this, hopefully not the day before the exam. Thank you guys so much, and I'll see you guys soon. Yeah. Bye bye. So. Boom.